Hey there, fellow Kagglers. We're always looking for an edge in competitions.
Always.
Well, today's deep dive, get this, is all about embeddings and vector stores.
Really fascinating stuff.
You sent us this incredible white paper, and let me tell you, it's packed with information, like how these tools can completely change how we handle massive data sets, the kind we see all the time, right?
Yeah, it's becoming so essential. Embeddings, in data science,
Mhm.
especially with these complex challenges in Kaggle competitions.
Okay, hold on. Before we go too far, can you just remind me, like, at the most basic level, what are embeddings, really? I know they're about representing data, like numerically, but
Mm.
it's always a little fuzzy for me.
Well, think of it this way. It's like we're translating
Okay.
real world data, right? Text, images, you name it,
Yeah.
even videos. We
Mhm.
translate that into a language that computers can work with.
Ah, interesting.
It's about turning that complex information into those numerical vectors. So computers can analyze and compare things in ways we just couldn't before.
So it's like we're teaching computers to read data the way we do.
Yes,
Not just ones and zeros, but meaning, relationships, all that.
exactly. And for Kagglers, this is huge. Like, think about it. Embedding speed up data processing storage, especially for those giant data sets.
We've all been there.
And they're at the basis for some seriously powerful tools, like retrieval systems, finding that needle in the haystack, recommendation systems, predicting what you're interested in. All this comes up constantly in competitions.
Okay, now that's making more sense. So the white paper goes into different types of embeddings. I'm guessing text embeddings are like the most common ones, right? Turning words and sentences into those vectors.
Yeah, definitely. Text embeddings are the most widely used, especially for natural language processing. And there are some cool approaches within that too, like take Word2Vec and Glove, for example. These algorithms, they learn to represent words, but based on their context.
So you are the company you keep kind of thing.
That's it. Words that show up in similar situations end up with similar embeddings.
Makes sense. So if I'm training on news articles, words like election, candidate, those would be clustered together, right?
Exactly. And then you've got fast text, which looks at subword information.
Oh, interesting.
Super helpful for handling those tricky words, like, out of vocabulary stuff, long scientific terms.
So it can handle even the tough ones.
Yep.
But what about representing whole documents? I'm guessing that's even more complex.
It is, and we've seen a real progression in the techniques, like earlier methods, TF-IDF, Doc2Vec. They use that bag of words approach. You just count how many times a word appears. But that misses a lot of the nuances.
So just knowing word counts doesn't give you the meaning, the connections between the words.
Right. But then we had this revolution, the pre-trained language models like BERT. These models, they're trained on just massive amounts of text data.
This is where things get really mind-blowing for me. All the hype about large language models, but I'm still trying to grasp how they actually work.
Well, BERT, for example, uses a transformer architecture. This lets it look at the whole context of a sentence. It's not just the word's individual meanings.
So it's more than just a bag of words. It's understanding the grammar, the flow of ideas.
That's it. And it leads to much richer document embeddings. And then we have models like T5 and PaulM emerging, even larger and more powerful, just pushing the boundaries of what's possible with language understanding.
It feels like an exponential curve of progress with these models.
Mm.
Incredible to think about the potential. Wait, but white paper doesn't stop at text, right?
Yeah.
It mentions image embeddings too. How do you even represent an image as a vector?
That's a great question. Convolutional neural networks, or CNNs, are kind of the stars of image recognition.
What?
They've been trained on enormous data sets, like think ImageNet, with its millions of categorized images,
Wow.
different objects, different scenes.
So by training on all that, the CNN learns to extract the important features that represent what's in an image.
Exactly.
But how do we go from those features to an actual embedding?
So once it's trained, the CNN can see the image, identify the key features, then those features are turned into a numerical vector. That's your image embedding.
So it's like the CNN is translating its visual understanding into something computers can use.
Precisely.
Wow, that's amazing. So you're saying we can now compare images based on their meaning, not just their pixels.
That's right. And it gets even more exciting. We're moving into multimodal embeddings, combining embeddings from different types of data. Imagine comparing an image to text, seeing how well they match in meaning. Even finding connections between audio and video data.
This is blowing my mind. Platforms like Vertex AI are making all this possible, right?
They are. It's opening up a whole new universe of possibility.
Okay, I'm officially blown away. This is all incredibly cool. But Gotta ask the practical question. What does this mean for us as Kagglers? We've got all these embeddings, but how do we actually use them to tackle those real-world problems we face?
That's where vector search comes in, those traditional searches matching keywords.
Yeah.
Well, vector search uses those embeddings to search by meaning, not just the words themselves.
So instead of searching for the word cat, I could search for documents that are about cats, even if they use different words like feline or kitten.
Precisely. Searching by meaning opens so many doors, especially with those diverse data sets you find in competitions, text, images, all mixed up. You can find connections that would be totally hidden with just keywords.
This is sounding like something out of a sci-fi movie.
Yeah.
But hold on, searching through millions, billions of embeddings, that can't be easy, right? The white paper mentions Approximate Nearest Neighbor Search, or ANN. Sounds pretty complex.
It can be, but the basic idea is balance, speed, and accuracy. We don't need the absolute nearest neighbor every time, just one close enough,
Yeah.
and we need it fast.
Especially with these huge data sets.
Right. Like imagine you're trying to find a book in a library.
Okay, I'm listening.
Instead of searching every single book, you have a system grouping them by genre, by topic.
Makes sense.
That's kind of what locality-sensitive hashing, or LSH, does with embeddings.
Okay.
It uses hash functions to group similar things. You can quickly narrow down the search.
Great analogy. So it's like dividing the library into sections. You don't search through everything at once.
Exactly. And then there are tree-based algorithms like KD trees, ball trees. They partition the search space either by dimensional boundaries or radial clusters.
Okay.
Makes it much faster to find those neighbors, especially when you've got lower dimensional data.
Okay, so we've got those methods to speed things up. But what about when we have those truly massive data sets, the high-dimensional ones? Those simpler methods, they wouldn't be enough, right?
Right. The white paper mentions a couple of more advanced algorithms: hierarchical navigable small worlds, or HNSW, and scalable approximate nearest neighbor, or STAN.
Those sound intense.
They are, but
Yeah.
they're built for those tough cases. Like
Yeah.
HNSW builds a hierarchical graph structure. Think of it like zooming in. You start with those long-range connections, then refine the search as you go deeper. Even in a huge data set, you find those close matches efficiently.
That's a cool way to visualize it. And what about SCAN? That one sounds like it's made for serious scale.
It is. Developed by Google, actually, and used in many of their products, including Vertex AI Vector Search.
So Google's using this to power some of the most demanding search stuff.
Yeah.
Impressive.
It's known for its ability to achieve both speed and accuracy, even when you're dealing with billions of embeddings.
So we've got these amazing algorithms, but they need a place to live, right? That's where vector databases come in.
Exactly. They're specially designed to manage and query those embeddings at scale. We need them to handle the unique challenges of working with embeddings, like making sure searches are fast, managing updates as your data changes, keeping things consistent.
So it's not just about storing them. It's about making them usable, searchable for real-world applications. The white paper mentions Vertex AI Vector Search. Makes sense with Google using SCAN. But it also talks about LODB and Cloud SQL Postgres. Those are more like traditional databases. How do they fit in?
It's interesting, actually. We're seeing this trend where those traditional databases are evolving. They're incorporating vector search functionality. So AlloyDB and Cloud SQL Postgres, they've added extensions like PG Vector, and they have native implementations of SCAN.
So they can do both, the traditional structured data and these new vector embeddings.
You got it.
That's pretty awesome.
But there are also those specialized vector databases. Pinecone, Weaviate, designed from the ground up for this kind of work. They usually use HNSW for fast search and have features like filtering and metadata management, all geared toward those embedding-based applications.
And for the open source fans, the white paper points to Weaviate and ChromaDB as well. It looks like there's a vector database for everyone.
There is, but picking the right one depends on a few things: the size of your data, the kind of queries you're doing, your budget, and your security needs.
Okay, before we dive into the really exciting part, the applications, I want to touch on a few operational things. The white paper calls it evolving embeddings. What does that even mean?
Good point. Embeddings, they're not static. As your data changes, your models get retrained, the embeddings need to be updated too. And this can be a tricky process, especially with those massive data sets.
So it's not just a one-time thing. It's an ongoing process of managing, maybe even getting rid of older embeddings to keep things running smoothly.
Yeah, exactly.
And within budget too, probably.
Right. Another point is that embeddings, they're not always the perfect solution. They're great at semantic meaning, but maybe not the best for literal or syntactic information, especially in very specific domains.
So if I'm looking for like a product ID or a piece of code, just using semantic similarity might not be the most accurate way to find it.
Right, in those cases, combining vector search with traditional full-text search is usually better.
Hybrid search. Best of both worlds. And last thing from the white paper, choosing your database based on the workload. Operational versus analytical, is that the main difference?
It is. For operational workloads, lots of reads and writes, a database like Cloud SQL might be good, but for those big analytical tasks, batch processing, BigQuery, with its vector search capabilities would be a better fit.
Okay, I think we've got a good foundation here. What, how, why of embeddings and vector stores. Now let's get to the fun part, the applications. What are we going to see?
We'll explore how embeddings are powering everything from search and recommendations to anomaly detection, and even the exciting world of retrieval augmented generation, or RA for LLMs.
Oh, can't wait for that. Stay tuned, folks. Things are about to get even more interesting. All right, I'm ready to hear about those applications.
Yeah.
The white paper talks about using embeddings to supercharge large language models, those LLMs everyone's talking about, through this thing called retrieval augmented generation, or RA. Sounds pretty futuristic.
It is cutting edge. RH is basically combining information retrieval with the generative power of LLMs, like giving LLMs access to this massive knowledge base outside of their own training data.
So instead of hoping the LLM just magically learned everything, we give it the tools to go find the information it needs on the fly.
Exactly. And this is important because, LLMs, as impressive as they are, they can sometimes generate things that are just wrong.
Yeah.
Factually incorrect, even made up. We call them hallucinations. And that can be a real problem when you need reliable information.
I've seen some pretty wild examples of LLMs going off the rails, confidently stating things that are just completely false.
That's where Archie comes in. It helps to ground those LLMs in facts. So instead of just relying on what they were trained on, they can access documents, data through a retrieval system. And guess what powers that?
Embeddings and vector search.
You got it.
So it's like giving the LLM a fact checker and a research assistant all in one. I see how this could be a game changer for tasks that need both creativity and accuracy. The white paper gives an example with question answering. Seems perfect for that.
Absolutely. Imagine you've got this huge collection of documents, research papers, manuals, whatever it is. You want to build a system that can answer questions based on that information. So first, you'd use embeddings to represent the documents and the incoming questions in the same vector space.
So you're creating embeddings for both the source and the query, just like we talked about with semantic search.
Right. And then vector search to find the documents that are most semantically similar to that question, pinpointing the most relevant information, even from tons of data.
So the LLM doesn't have to read everything. It just gets the most useful stuff right away.
Yeah.
What happens then?
Those documents, along with the original question, you feed those to the LLM.
Okay.
Now it has that extra context to generate a much more informed and accurate answer.
Like giving it the evidence to back up its answer. I love that. The white paper mentions that RAG can even give the sources for the LLM's response. So much more transparent, trustworthy.
It is crucial, especially when you need that accuracy, that verifiability. By including the sources, you can see where the information came from, check how credible it is.
Footnotes for an LLM's essay. The white paper even walks through this simplified example. Using Vertex AI LLM text embeddings, Vertex AI vector search, and a library called LangChain. It makes it seem like implementing this kind of system isn't too hard.
It is getting more accessible, yeah. These tools and libraries are taking care of a lot of the complexity. Developers can focus on the logic of their applications, and the example, it shows you how to answer a question based on just a few documents. You see how the LLM uses that retrieved context. It's a good starting point to understand how RAG works.
Okay, now I'm definitely curious to try this out. But before we go too far, I want to rewind a bit. Training embeddings, the white paper says it can be, well, complex and computationally intensive. Always makes me a little nervous.
It can be, especially if you're starting from scratch. But resources like TensorFlow Hub and Vertex AI are helping a lot, even for those of us without those huge computing clusters.
So TensorFlow Hub has these pre-trained embedding models you can use right away, or fine-tune on your own data if you need something more specific.
Exactly. And Vertex AI gives you a whole platform to train and deploy your custom embedding models. Handles a lot of the infrastructure stuff so you can focus on the data science.
Huge relief. Much rather be exploring data than messing with servers.
Ugh.
But regardless of the platform, the white paper says the general process often uses this dual encoder architecture and something called contrastive loss. Sound a little intimidating.
They might sound complex, but the ideas are actually pretty intuitive. Think of it like two towers.
Towers.
Yeah, each one encodes a different kind of data. So one might encode queries, the other documents, or one encodes images, the other their descriptions.
Two specialized translators, each handling a different type of input.
That's a great way to think about it. And then contrastive loss, it's a way to train those encoders. You want to pull similar embeddings closer while pushing dissimilar ones apart.
So if it's a question and a relevant document, the embeddings should be close in the vector space.
Right.
But if it's a question in some random document, those embeddings should be far apart.
Exactly. And by training with this objective, the model learns to make embeddings that really capture the meaning, the relationships between different data points.
So cool. The white paper also mentions pre-training and fine-tuning. Seems to be everywhere in machine learning these days.
It is. Pre-training means you train a model on a massive data set, usually unlabeled, give it this general understanding of the data. Then you fine-tune it on a smaller data set, labeled this time, that's specific to the task you want it to do.
So for embeddings, you might pre-train on a massive corpus of text, like all of Wikipedia or tons of images from the internet, and then fine-tune it on like a data set of questions and answers, or images and their descriptions, depending on what you're doing.
Exactly. You get the benefit of that huge pre-training data set while still tailoring the model to your specific need. It's very powerful.
This is all incredibly powerful, but I gotta admit, I'm still picturing how this plays out in the real world. Can you give me a concrete example? How are embeddings and vector stores actually being used to solve a problem?
Sure. Let's say you want to build a semantic search engine for a website that sells clothes.
Okay, so instead of just searching for blue dress,
Right.
I could search for something like a dress perfect for a summer wedding or a casual outfit for brunch.
Exactly. First, you create embeddings for every product. You could use a pre-trained text embedding model based on the descriptions, or even train your own model that takes into account the images, customer reviews, all sorts of data.
So each product gets its own embedding capturing like its essence.
Right. And you store all those in a vector database. Then, when someone searches, you embed that query using the same model.
So now you have an embedding for the query in all those product embeddings. What next?
You use vector search to find the product embeddings that are closest to the query embedding. The most similar ones are the most semantically similar to what the person's looking for.
So even if they don't use the exact words in the description, the engine gets their intent and shows relevant results. It's like the search engine understands fashion.
That's the power of it. We go beyond keyword matching, build systems that understand meaning.
Next level search engines, more human-like.
Yeah.
I love it. And this isn't just for text, right? The same idea for images, videos, audio, anything you can make an embedding for.
Absolutely. So many possibilities. Searching for images based on like a description of the scene or the emotions it evokes, finding music that matches a certain mood. Embeddings open up completely new ways to interact with information.
Okay, now I'm really getting it. What other applications are out there using these techniques?
Recommendation systems are a big one. Instead of just using explicit ratings or just past purchases, you can use embeddings to represent users and items in the same vector space.
So you could make user embeddings based on their browsing history, their purchases,
Yep.
their interactions with others, even their social media stuff.
Yeah,
And for items, you could use product descriptions, images, reviews, all of it.
exactly. And then, just like with search, vector search to find items that are closest to a user's embedding. So you're recommending things that are actually aligned with their interests.
This could make recommendations so much better than what we see now. No more suggestions for stuff I would never buy.
That's right. And it helps with the cold start problem. When you have very little data about a new user or a new item, even then you can still make decent recommendations based on the semantic relationships, even without much historical data.
Huge advantage. It's like the system can make educated guesses based on patterns and relationship.
That's it. And this idea of using embeddings to uncover those hidden relationships, it's also used for anomaly detection. Say you're monitoring sensor data from some equipment, you create embeddings for each sensor reading capturing the normal operating conditions.
So you're making a fingerprint of normal behavior.
Yeah.
What if something goes wrong?
You see a new reading, its embedding is way off from the cluster of normal ones. That could signal an anomaly, Like the system is saying, this isn't right.
So it's spotting deviations from the norm, even if it doesn't know exactly what kind of anomaly to expect.
Right. And this can be used for all kinds of data: financial transactions, network traffic, social media. Anywhere you're looking for those unusual patterns, embeddings can help.
Embeddings and vector stores are changing how we use data across so many fields. So like they give us this new way to see things. But with any powerful tech, there are things to be careful about, right?
Definitely. There are always trade-offs. Vector databases are great for some queries, but they might not be the best fit for every situation.
Right.
Traditional databases are still really good for structured data, complex queries with lots of filtering, that kind of thing.
So know your tools, pick the right one for the job. And as our data sets get bigger, models get more complex, we also need to think about the computing power needed to run all this.
It's all about finding that balance, performance, cost, complexity. Luckily, cloud platforms are making it easier and more affordable to access that power.
Okay, we've covered a lot, technical details of embeddings and vector stores, some really cool applications, and even some things to watch out for. Feeling pretty excited about all this. What are some key takeaways for our listeners as they explore this stuff?
I think the biggest thing is that embeddings and vector stores are incredibly versatile, and they're changing how we work with data very rapidly.
It's like they give us this new way to see things. They allow us to move beyond traditional methods and build systems that understand meaning and context.
And that's a big deal for so many applications: search, recommendations, anomaly detection, even how we interact with LLMs.
But it's also important to remember that there's no single perfect solution.
True. The best approach depends on the problem, the data, and the resources you have.
Great advice. This deep dive has really opened my eyes to what's possible with embeddings and vector stores. Any resources you recommend for those who want to learn more?
Well, the white paper you sent is a great starting point. Gives you a good overview of the concepts and techniques.
Yeah.
There are some good tutorials and courses online too, step-by-step guides for working with embeddings and vector stores.
And platforms like TensorFlow Hub and Vertex AI give you that hands-on experience. You can play with pre-trained models, build your own solutions.
Exactly. And don't forget the community. Researchers, practitioners pushing the boundaries of what's possible. Lots of blogs, articles, open source projects out there.
Whole world to explore.
Mm.
Well, I think it's time to wrap up this episode. It's been an incredible journey into the world of embeddings and vector stores. But before we go, I have one final question for you. With all this talk about LLMs, getting so much smarter, so powerful, do you think embeddings and vector stores are like essential going forward? Or will LLMs just, I don't know, figure out how to do all this stuff themselves eventually?
It's the million-dollar question, isn't it? Lots of debate about it right now.
Yeah.
Some people, they think embeddings and vector stores are going to be critical, like
Right.
how we keep those LLMs grounded, prevent those hallucinations.
It's like we need to tie them down to reality. Embeddings are the anchor. Yeah.
Yeah, good way to put it. But, there's the other side. Some researchers, they think LLMs might just evolve,
Oh, wow.
build in that functionality of embeddings and vector stores internally.
So no more separate systems. The LLM would just handle it all.
Huge leap if it happens. But
Yeah.
we don't know yet if that's even possible, technically, or even if it's what we want. A lot of open questions: how to design, how to train these systems, and, the risks involved.
They're still figuring out LLMs, what they can do, what they can't.
It's early days, really.
Such a fascinating time to be in this field, though.
Absolutely. Like witnessing the birth of something completely new, computing, information. It's all changing, exciting, and a little scary, too.
Totally. Well, I think that brings us to the end of our deep dive. Embeddings and vector stores, incredible stuff. And I have a feeling we're just at the beginning.
Oh, yeah. Just scratching the surface. This tech has the potential to, revolutionize so many things. Industries, applications, you name it.
Huge thanks to our expert for walking us through all this. It's been a pleasure learning from you.
Likewise. Always fun to chat about this stuff, especially with someone so engaged, asking such great questions.
And to our listeners, definitely check out the resources we've mentioned. This is a fast-moving field, so stay curious. Maybe you'll be the one to make that next breakthrough in embeddings and vector stores. Until next time, keep on Kaggling.